All right. All right, so for a single variable function, let's get started, folks. For a single variable function, we have an extreme value theorem. The extreme value theorem tells us that a continuous function obtains a maximum and a minimum on a closed interval. So if we look at some closed interval of x, then in that interval, a continuous function is going to have a maximum value and a minimum value. We have something similar for a multivariable function. So if I'm just going to talk about a two-variable function here, but it's any multivariable function. If z equals f of x, y is continuous, then f of x, y will have at least one maximum value and minimum value at least one point let's see, what do I want to say? At least one maximum and minimum value. I already said at least, so I'm going to erase this and say in a closed bounded region. So when we talk about relative extrema, we're talking about in some kind of region. And closed, just a reminder, closed means that the region contains its boundary, contains its boundary points, and bounded means that the region doesn't grow, isn't infinite. We have a closed bounded region. So we have a similar thing to our extreme value theorem. We're going to have at least one maximum and at least one minimum in a closed bounded region. So let's, for a multivariable function, let's define a relative or a local maximum and minimum. So we have a good idea of what a maximum and minimum mean. I just want to make it a little more formal. F of x, y has a local maximum at some point AB if f of x, y is less than or equal to f of AB for all x, y in a closed bounded region. I'm going to say in an open disk. About AB. So this is just saying that around this particular point, f of AB is the biggest value. Might not be everywhere, but around that point, AB, that's the maximum value. And f of xy has a local minimum. We just turn around this inequality. We have a local minimum at our point if our function is bigger than the function at f of a, b in an open disk around a, b. So if you have a if you had a plane, like a horizontal plane, then every point on the plane would be a maximum and a minimum. So it can be equal. So what this is telling us, what local maximums and the local minimums tell us about is how the function compares to nearby values. And nearby just means we define our nearby as how big we make our disk. And we're going to define critical points in a way that's very similar to what we did for a single variable function. So we know that in a bounded region that our function is going to obtain a maximum and a minimum, at least one. Well, let's talk about how we find them. F of xy has a critical point, and we've talked about this, we've kind of built this up. So we have a critical point at some place, AB, if the partial derivative with respect to x at that point equals the partial derivative with respect to y, and they both equal 0. Or if one or the other does not exist. Mm-hmm. And we can show, we're not going to do it, but we can show that relative extrema occur only at critical points.
So are we ever going to really be asked to find local minimum and maximum of multivariable function?
Yes, that's what we're building up to, is how we go about doing
Well,
that.
no, but like this part where like we don't necessarily have to have a relative extreme, like the part just before critical points.
Here, where we were just defining a local maximum, local
So
minimum.
basically, all it says is you have to have a critical point.
Yeah,
Oh, okay.
we were just defining what we meant by a local maximum, local minimum,
Oh,
and then we're saying we find those at critical points. And we've seen at critical points, and we've seen that if both f sub x at a particular point and f sub y at AB are both 0, then the gradient at AB equals a 0 vector. And that tells us that every directional derivative is 0. And that also means that the tangent plane is horizontal. So all of these things are equivalent ways of talking about a relative extrema. The first partials are both 0 at the same point. The gradient is 0 at that point, because that's the same as saying the first partials equal 0. Every directional derivative is 0 at some point. Tangent plane is horizontal at some point. All of those things mean we're at a relative extrema. So we said this before, but just like for a single variable function where the tangent line is horizontal at a relative extrema, the tangent plane for a multivariable function, the tangent plane is horizontal at a relative extrema. So we find a relative extrema by setting the first partials equal to 0. That usually is going to involve solving some kind of set of simultaneous equations. All right, let's look at a quick example. This one was, I liked the setup for this one better when before we got new books. Because in the old BC textbook, in the homework problems, they would say, I'm going to write it down. We want to find,
Is that a 9 or 2?
this is a 9. Find any relative extrema. So the old book in the homework would have little things that said this. Be clever. And the students hated it.
Yeah, I would too.
Yeah. And then then it would say surprised. Anyway, so can we be clever about this and find the extrema without doing any calculus?
No.
What?
Like we could think about it.
Well, what would this surface be?
Is that 3 negative 2?
Like one of these.
That would be a.
Is that 3 negative 2? Is that the,
It would be.
that's the point of the
It's like a
ellipsoid?
parabola.
Yeah, this is a
Paraboloid.
this is a paraboloid. Opens upward or downward?
Downward.
Opens downward.
So it's like a parabolic.
So the extrema is going to be at the vertex, and what at 3 negative 2? And what's the function value at 3 negative 2? 9. So we have a relative max.
Wait, hang on. Why is it up and down? So just move everything over. It's like everything positive.
We have z equals
said
9
equals
minus
to
9 minus x squared. Z equals 9 minus x squared, essentially. Relative max at 3 negative 2, which is the vertex. So the relative max is g of 3 negative 2 is 9.
Or could you say 3 negative 2, 9?
Sure.
And then
Yeah, you could say our point is 3 negative 2, 9. The extreme value of the function is 9. Let me see if I have. Yes.
Run a test and we see that. Can we do that clever thing? Or
If you explained it, if you say this is a parabola that opens downward, the maximum is going to be at the vertex, that'd be fine. What is this? 13.8, part 1? Yeah.
Oh, boy, a surface.
So while that opens up. All right. Just like for functions of a single variable, a critical point does not always give us an extreme value. Because for a single variable function, we have inflection points, right? Where the concavity changes. For a multivariable function, we have what we call saddle points. So I'm going to say,
That's like really.